Some cargo ships stretch longer than the Eiffel Tower is tall. Loaded, they weigh more than 300 fully fueled jumbo jets. Their engines stand 3 stories high. Their propellers are larger than most houses, and yet, every few years, engineers do something that sounds physically impossible. They lift these giants completely out of the ocean, not to scrap them, to repair them. There is no crane on Earth strong enough to pick up a fully loaded car carrier. No machine that can roll a 200,000-ton tanker into a workshop. No system that lets you simply pull one apart and put it back together. So how do engineers inspect, repair, and rebuild ships bigger than skyscrapers without taking them apart and without stopping global trade in the process? The answer is one of the least visible and most demanding engineering operations on the planet. Chapter 1. Why ships can't stay in the water forever. Every ship afloat is under constant attack, not from storms, from something slower, quieter, and far more relentless. Saltwater begins working on steel the moment a vessel touches the sea. Below the waterline, marine organisms colonize the hull almost immediately. Barnacles, algae, and shellfish layer over each other until a smooth surface becomes rough, uneven drag, forcing the engines to burn dramatically more fuel just to hold the same speed. Underneath that growth, corrosion quietly thins the plating that holds the entire structure together. And this is not damage anyone is allowed to ignore. Classification societies require a full structural inspection on a fixed schedule. Miss one, and the vessel legally loses its certification to sail at all. Which brings engineers straight back to the impossible part. You cannot inspect steel you cannot reach. You cannot weld new plating underwater. You cannot measure a hull that is submerged under thousands of tons of ocean. So before a single repair can begin, engineers have to answer one question that sounds absurd on its face. How do you remove a 200,000-ton ship from the ocean? Because everything below the waterline is waiting on that answer. The propeller, a single casting weighing more than 30 tons, has spent millions of nautical miles losing the exact blade geometry that makes it efficient. The rudder has absorbed years of hydraulic stress. Tail shafts have worn against their bearings. Sea chests, ballast tanks, and underwater valves have corroded voyage by voyage. Every one of those components sits in the one place on the ship that no one can reach while it floats. Chapter 2. Emptying an ocean. If you cannot lift the ship, there is only one option left. You remove the water around it. That sounds simple until you consider the scale. Engineers need an artificial basin long enough to hold a vessel stretching 3 soccer fields end to end, deep enough to float it in, and strong enough to hold hundreds of thousands of tons once the water is gone. This is the dry dock. Some are graving docks, permanent basins carved into the shoreline and sealed with enormous gates. Others are floating dock, submersible steel structures that sink beneath the ship, then rise underneath it like a mechanical elevator. Either way, the operation begins the same. The vessel is guided into position with almost no margin for error, assisted by tugs, winches, and divers working below the surface. Then, the pumps start. Millions of gallons of seawater are removed over several hours, and as the level drops, the ship slowly settles onto a grid of docking blocks arranged across the dock floor. And this is the single most dangerous moment of the entire operation. Those blocks are not placed randomly. Engineers calculate their exact positions in advance, mapping them against the ship's internal frames so the load transfers through the strongest parts of the structure. Get that calculation wrong, and the vessel's own weight becomes the enemy. A misaligned block can concentrate thousands of tons onto a single unsupported section of plating and crack the very structure the repair was meant to save. So ballast levels, draining speed, and block placement are all locked in long before a single valve opens. Then, the water disappears, and something genuinely strange happens. A machine built to spend its entire life supported by the ocean is suddenly standing on dry land, fully exposed for the first time since it left the shipyard. The hull is finally accessible, but from the second the last of that water drains away, a new problem has already started. The clock is running. Chapter 3. Repairing a floating skyscraper. With the hull exposed, the true scale of the vessel becomes impossible to ignore. Standing beneath a car carrier in dry dock feels less like inspecting a boat and more like walking underneath a fallen skyscraper. Workers at the keel look like specks. The propeller alone towers over the people sent to remove it. But before anyone cuts a single piece of steel, engineers have to answer a question most viewers never think to ask. Is the ship still the shape it was built as? Because after decades at sea, it usually isn't. Teams laser scan the entire hull, capturing millions of measurement points, then compare that scan against the original shipyard geometry. Years of wave loading, cargo cycles, and thermal stress can leave a vessel subtly deformed, bent by fractions of a degree along its length. Repairing a ship to the wrong shape is worse than not repairing it at all. Only once that survey is complete does the physical work begin. High-pressure abrasive blasting strips away old paint, corrosion, and marine growth across tens of thousands of square meters of steel, revealing exactly how deep the damage runs. And what they find creates the next problem immediately. Where corrosion has eaten too far into the plating, there is no patching it. Those sections have to come out entirely. But cutting a house-sized plate out of a hull removes part of what holds the surrounding structure up. So before the torches start, engineers install temporary steel supports inside the vessel, bracing the frames around the opening, then monitor hull stress as the section is lifted away. Remove too much at once, and the structure around it begins to move. New steel is welded in, and the protective coatings go back on. Modern anti-fouling systems, including self-polishing copolymer paints and silicone release coatings, are engineered to stop organisms attaching in the first place, protecting both the steel and the ship's fuel efficiency for years. At the stern, the propeller is disconnected and drawn off, then inspected for cracks invisible to the naked eye, often using X-ray scanning, because a flaw missed here becomes a catastrophic failure in open water. Reinstalling it is harder than removing it. The propeller shaft has to be aligned to tolerances measured in fractions of a millimeter across a shaft line that can run the length of a city block. Misalign it, and vibration will destroy the bearings within months of sailing. Some owners use the same window to retrofit new technology entirely, installing exhaust scrubber systems or energy-saving devices designed to squeeze more efficiency out of a hull that may sail another 20 years. Every one of these jobs solves a problem created the moment the ship last left dry dock, but none of them happen fast, and that becomes the next crisis. Chapter 4. The Race Against Time. A ship sitting in dry dock is not earning money. It is losing it. Every additional day can mean tens of thousands of dollars in lost freight revenue, canceled bookings, and delays that ripple outward through supply chains, expecting that vessel to be somewhere else entirely. So the moment the water is gone, the operation stops being purely technical and becomes a war against the calendar. Hundreds of workers move through the same confined space at once. Welders, blasters, painters, electricians, riggers, and inspectors, frequently in 24-hour shifts to keep progress continuous. And that crowd creates a problem of its own. The work cannot happen in any order. Blasting has to finish before painting can start. Paint has to cure before the propeller goes back on. Steelwork has to be certified before compartments are sealed. Tanks have to be gas-free before anyone enters them. One delay in one task cascades through everything downstream, pushing the ship's departure back by days. Shipyards answer this with parallel operations, dividing the vessel into zones so multiple trades can work simultaneously without blocking each other, coordinated hour by hour against a schedule locked in months earlier. Repairing a ship this size, it turns out, was never only a technical challenge. It was a logistics challenge wearing an engineering disguise. Chapter 5. Making a giant ship seaworthy again. Eventually, the scaffolding comes down, the dock floods, and the ship lifts clear of the blocks it has rested on for weeks. And now every decision made in that dock faces the only judge that matters. Weeks of engineering work come down to one question. Did the ship leave stronger than it entered? Nothing in the dry dock can answer that. Pressure tests confirm seals hold, steering gear cycles correctly, engines run, but no shipyard on Earth can simulate the load of a fully laden hull driving through open ocean. There's only one way to find out: sea trials. The vessel sails out under its own power with engineers aboard, instruments recording everything, vibration through the shaft line, fuel burn against predicted curves, propeller performance under real load, course stability across long runs. This is where a misaligned shaft reveals itself, where a hull repaired to the wrong geometry starts pulling off course, where weeks of precision work either holds or does not. If the numbers come back wrong, the ship goes back into the dock and the entire schedule collapses. Classification surveyors review every result before certifying the vessel seaworthy. Only then is the repair actually finished. Final chapter, the engineering nobody sees. Most people who watch a cargo ship cross the horizon never think about what keeps it out there. They see the vessel. They never see the system that makes its survival possible. And that is the twist buried underneath this entire story. Repairing the ship was never the hardest part. The hardest part was creating a place where engineers could work on something that was never designed to leave the water. An artificial environment capable of holding a machine the size of a skyscraper perfectly still, perfectly dry, and perfectly supported for weeks at a time. The dry dock is not the setting for the repair. The dry dock is the engineering achievement. Every hull scanned, every plate welded, every propeller aligned depends entirely on it. Without dry docks, corrosion and fouling would take every large vessel out of service, and global shipping would slowly grind to a halt. Modern cargo ships may be among the largest machines humanity has ever built, but keeping them alive for 20, 30, even 40 years demands something arguably harder than building them. It demands that engineers recreate over and over the one condition these giants were never designed to survive: standing completely still, out of the water, exposed to the people rebuilding them piece by piece. So the next time you see a ship on the horizon, remember what you are actually looking at. The world sees the ship. Engineers built the machine that keeps every one of those ships alive.